Namaste, hello everyone, welcome to this session. So, in this session we are going to solve some examples on the topics we studied in lectures 18 to 19 of this course on experimental model analysis. The topics we studied in these lectures are aliasing, quantization and windowing, leakage and window functions. So, please watch these lectures to know the background theory of the examples we are going to solve in this session. So, let us get started with the first example. Let me go to next page. Example 1. So, the first example is like a harmonic signal with an amplitude of plus minus 12 volts is to be measured. There are three choices for the maximum input voltage range of measurement, right, and if these are plus minus 10 volt, plus minus 20 volts and plus minus 30 volt, then which is the most suitable input voltage range that should be used from the viewpoint of minimizing the quantization error. Okay. So, this is the problem. So, let us solve this problem. So, essentially we have a harmonic signal of amplitude plus minus 10 volt, and when we make measurement using any analyzer or a data acquisition system, we need to decide the maximum input voltage range which is allowed, correct, and three choices are given here which are available for selection: plus minus 10 volt, plus minus 20 volt and plus minus 30 volt, and then we have to choose the most optimum choice, right, for our measurement, right, for measuring a signal whose amplitude is plus minus 12 volt, correct. So, in fact, the theory of this we have studied in the lecture classes when we talked about the quantization, correct, and when we take the measurement depending upon the number of beats of the ADC, there would be certain number of quantization levels. So, if n is the number of beats of analog to digital converted ADC, right, and if plus minus V max is the maximum voltage range, right, which we have chosen, right, the maximum allowable voltage range, the input voltage range, then the quantization interval delta V is equal to twice V max upon 2 to the power n. This is quantization interval. So, this we have studied in the lecture class, right. So, therefore, we see that the if we choose V max, the maximum voltage range, to be too large, which is not required for the measurement, then what is going to happen, the quantization interval will be very large and then it will lead to higher quantization error. So, that is why as we discussed in the lecture classes, the best strategy is to choose V max which is just optimum, right, which is just optimum to enable the measurement of the voltage under consideration, the voltage signal under consideration. So, let us now take each of these options one by one and see that which one is most appropriate. So, let us say if we take the option 1, right, let us say we take ranges plus minus 10 volts. If we choose that, and let us try to show through figures what is going to happen if we choose this particular range. So let us say that we have this signal here like this, correct, and if I now show the signal here, let us say plus minus 10 volt, something like this. So, this is the signal we have to measure, right, x, and then what is the maximum allowable voltage range. So, of course, this amplitude here is 12 volt, right, this is plus 12 volt and this is minus 12 volt. So, that is the signal we are trying to measure. And what is the input voltage range? The input voltage range is plus minus 10 volt. So, I am drawing two horizontal lines to represent that, something like this. So, this is plus 10 volt and this is minus 10 volt. So, when we now perform measurement using this option, what is going to happen? The signal which is above 10 volt, it will be truncated, okay, by the by the input voltage end of the analyzer. ADC will truncate or chop off this signal. Right? So, the signal which will be left with us after measurement would be something like this. The signal we will be left will be I am showing in green this signal which we have measured, and you can easily see that now this signal is not the correct representation of the actual signal which we wanted to measure. It has been truncated, chopped off, right. So, you can see signal truncation, right, and this signal truncation is not desired because it is distorting the signal, correct. So, when we analyze such a distorted signal, obviously the information that will be revealed will not be representing the true signal. So, this is not desired. Correct. So, this is essentially overloading the analyzer end. The allowable range is plus minus 10 volt, but signal level is more than that. So, basically overloads the analyzer. So, causes overloading of the input end of the analyzer. So, this option is ruled out, we will not take this option, right. Let us see now the option 2. This is plus minus 20 volts. Now, in this option what is going to happen is that we have this, again I will draw the signal like this, which is the 10 volt signal like this, and now this time the voltage, let me mark this voltage here, this is plus minus 12 volt and this is minus 12 volt, right. And now if I mark the voltage here, this voltage is 20 volts, right. So somewhere somewhere here, something like this. So very approximately I have marked it. So this is plus 20 volt and this is minus 20 volt, right. And now here you can see that the signal will not, the input N will not be overloaded and there will be no signal truncation. No signal truncation, right. And also the maximum voltage is 20 volt, which is more than 12 volt, right. And of course therefore there will not be any no signal truncation, and also the quantization error also will not be large, because signal level is not too low than the maximum range, right. So that is why this is something not lead to too much of quantization error. Quantization error will not be large. So this is something we can accept, right, this we can accept. So now let us go to talk about the third option. I will go to the next page. If I look at now option 3, plus minus 30 volt, and now if again I draw the signal, right. So maybe I can write little on lower side somewhere here. Something like this. So this is plus 12 volt and this is minus 12, right. And now if I also show the voltage range, then the voltage range is somewhere here, something like okay, this is minus 30 volt and this is plus 30 volt, correct. So now in this case what is going to happen, the maximum voltage 30 volt is much larger than 12 volt, right. So in relative terms, if you compare with the voltage range plus minus 20 volt, this particular voltage range will lead to a higher quantization error, correct, because the quantization interval will be wider here, delta V, which we discussed on the last slide, right. That quantization interval will be larger here, and hence the quantization error will be higher in this case. So it will have higher quantization error. Of course, there will be no signal truncation, but relatively it will have higher quantization error, correct. And that is why among the three, plus minus 20 volt is the best option to go forward, to go ahead with, right, and hence that should be used in this case. So this basically completes our solution of example number 1. We go to example 2 now. Let us go to next page. Example 2. Question: a signal xt is given below. The signal xt is given below and is to be measured. Choose record length T of measurement to avoid leakage with a rectangular window. Right, and the signal that is given is x of t is phi cos 2 pi 6.5 t minus 30 degree and plus 8 sin 2 pi 10 t minus 45 degree. Okay. So, this is the problem, let us solve this. So, let us try to understand the problem first. A signal has been given, right, which is to be measured, and then obviously the signal amplitude, frequency, phase all are are easily known from the signal, right. We can see the signal, the frequency is 6.5 hertz, other is 10 hertz, amplitude is 5 and 8 and phase is 30 and 45 degree, the phase lags. And this has to be measured now using a rectangular window, means no artificial window function has to be used. As I explained in the lecture class, not using any artificial window function essentially amounts to using a rectangular window. Just merely the process of starting and stopping the measurement process amounts to multiplying or is equivalent to multiplying the signal to be measured by a rectangle window function, right. And hence we say that when we do not use any window function, we say that we are using rectangular window, right. So, therefore, now here the task is that we must choose the record length t such that the leakage is avoided. Okay. So then how to choose that, right. So, as I explained in the lecture, if we know the time period of the function or time period of the signal which is given, and if the signal is periodic, then for a periodic signal, if we know the time period of the signal and if we choose the record length which is integer multiple of the time period of the signal, right, then we do not have to use any window function, right, and then leakage would be avoided with such a choice of the record length. So, that is the principle we are going to use to solve this problem, correct. So, let us see what are the frequency content of the signal. So, here we see that if we look at the first frequency is there are two frequency components, one is at 6.5 hertz and other is at 10 hertz, correct. So, what is the time period of this? So, obviously I can write the time period of this signal as 1 upon f1, correct, which is 1 upon 6.5 seconds, that is the time period of the first frequency component, and time period of the second frequency component is 1 upon f2 is equal to 1 upon 10 seconds, right. So, now we must choose a record length t such that an integer number of cycles of both these components are completed in that time t, right. So, let us say that a time period of measurement is t, right. Let us say t, let t be the record length, right, of measurement. So, then for completing integer number of cycles of f1, we can then say that t is equal to n into t1, correct. T should be equal to n into t1. So, n is the number of cycles of frequency f1. Similarly, for second frequency m number of cycles may be completed. So, we can write t is equal to m into t2, is not it. So, that is why, and therefore, we then have T1 into n should be equal to T2 into m, correct. Okay. So, in that case then what result we get? We get n is equal to T2 upon T1 into m, right, and which of course also can be written as F1 upon F2 into m, right. So, it means now we have to choose n and m as integers, that is important. So, we have to now choose n and m integer values, right. Okay. If we are able to do that, then obviously it would lead to completion of integer number of cycles of both the frequency components f1 and f2 in time period t. So, let us try to choose those values. So, if I now substitute say n in place of f1, then I write 6.5 and f2 is 10. So, it is equal to m. So, now if I make choice, let us say if I take m is equal to say 1, right, m is equal to 1, that is the lowest possible integer I can choose, non-zero integer I can choose, then in that case n is equal to 6.5 by 10. Now, this is not an integer, see, not an integer, right. So, this value is something I cannot choose. Similarly, if I take m2 is equal to 2, then n will be equal to twice 6.5 divided by 2, this is also not an integer. So, therefore, you would see that if I choose now m2 is equal to, if I take 10, then n would be 6.5, which again will not be an integer. So, if I choose m2 as 20, then what that would give us 20 into 6.5 upon 10, that gives me 13. So, now n is equal to 13 is an integer. So, it means the lowest value of integer values would be 20 for m and then and 13 for n. So, obviously I think I should not put here the subscript here m which I have written here, sorry, it should be simply m, not m1 m2. Okay, so let me correct that m. Okay, so it means that now I can have the values as, therefore m is equal to 20 and n is equal to 13, which means that what will be t now? T would be then equal to t would be simply equal to m into m upon f2, correct. T would be simply m into t2, which is basically m upon f2. So, 20 upon f2, which is 10. So, t is equal to 2 seconds. So, it means that the minimum record length, minimum t is 2 seconds, minimum t is 2 seconds. So, if I now choose a record length of 20 of 2 seconds, then it would not lead to any leakage, because this signal x of t, it repeats it repeats after 2 seconds. So, if I choose one record of this signal and then analyze it, there would be no leakage, right. Also of course, if I take integer number of these records, if I take 4 seconds, 6 seconds, 8 seconds, which are all integer multiples of the minimum record length 2 seconds, then also there would be no leakage. But if I take a record length which is not integer multiple of 2 seconds, it would lead to leakage, right, and then you would see spurious frequency components appearing in the frequency spectrum, correct. So, obviously because remember that the frequency resolution I would get with this minimum t is 0.5 hertz, right, 1 upon 2, 0.5 hertz. But if I want a frequency range of, let us say, higher frequency resolution, let us say 0.25 hertz, then the option to me is that I can increase the record length, then I can increase it to, let us say, 4 seconds. If I increase to 4 seconds, not only the leakage would be avoided, but also a resolution of which is improved resolution of 0.25 hertz would be obtained, correct. So, I think this is how this would lead to would avoid would not have any leakage in the spectrum with a rectangular window, right. So, this way we complete the solution of example 2. Let us go to example 3. Let me write the question first. Example 3. Question: a signal given below is to be measured. Identify the amplitude, frequency and phase of all the frequency components in the signal. And then part B of the question is choose a suitable sampling frequency for measurement, right. So, let us solve this problem now. Right. So, let me route the the signal which is given to us. X of t is equal to 8.0 plus 7 sine 2 pi 2 t plus 4 cos 2 pi phi t plus 8 cos 2 pi 16 t. So, this is the signal problem given. So, what this problem is all about, that there are two tasks in the problem. In part A, we are supposed to identify from the given signal what are the frequency components which are present, their frequencies, amplitude and phase, correct. That is what we have to do, first task. And then part B, we have to choose a suitable sampling frequency for the measurement. So, let us first look at the task A. So, part A. So, let us now make a table that would be convenient. We have right here the frequency in hertz, right, and then let us write the amplitude and then write the phase, and here we can see the serial number like this. Okay. So, the first component is, you can see we see on the right hand side 8. So, 8 means it does not vary with time, it is a constant component, and that is called DC component. So, the frequency of this component is 0 because it does not vary at all, right. So, therefore, you can roughly say that the frequency is 0 means its time period is infinity, because time period is 1 upon f, right. So, this component varies after infinite length of time, that is how it can be interpreted as. So, the frequency of this component is 0, this also we call as the DC component. correct, and the amplitude of this component is 8 and the phase of this component is 0. So, that is the first component. Then we have the first component. Now, let us look at next one 2. If you look at the second term, it is 7 sin 2 pi 2 t. So, the coefficient of t is the frequency in radians per second. So, the radian per second frequency of this component is 2 pi into 2 radian per second, but 2 pi f is the expression for the radian per second frequency. So, that is why 2 is nothing but the frequency in hertz. So, we say that the frequency of this component is 2, right, 2 hertz, and the amplitude, that is the 7, that is the amplitude, and then this phase. Now, this sine component, it has it basically lags the cos component by 90 degree, right, because the maximum value of the sine wave reaches after 90 degree of phase, right, with respect to the cosine wave, and that is why its phase lag, it lags the cos component by 90 degree. So, we say that its phase is 90 degree. Then the third component is 4 cos 2 pi phi t. So, phi is the frequency of this component, the amplitude is 4, correct, and it is a cosine wave. So, its phase is 0 degree phase. Okay. Then we have the component, one more component there, right, and that component is 8 cos 2 pi 16 t. So, the frequency is 16 hertz, right. So, 16 hertz, amplitude is 8, and again it is a cos component. So, its phase is 0 degree. So, in this way you can see we have basically made this table which shows at a glance all the frequency components with their frequencies, amplitude and phase. So, this exercise basically guides us that how we are supposed to interpret a signal, correct, and of course, when we measure a signal, what we measure is x of t, we measure x of t. The right hand side shown in this example for the signal is actually not known to us or given to us in practice, but then through discrete Fourier transform, right, we can basically obtain the right hand side, right, and one example of that we saw in the previous session, that how do you obtain DFT and then you get the frequency, amplitude and phase of different frequency components. Okay. But then that is how we can interpret those components. Let us now look at the part 2 of this problem, B part. So, choose sampling frequency. Now, in the lecture classes we studied that what guides the choice of natural frequency of the sampling frequency, that we studied what is called as Nyquist sampling theorem, right, Nyquist sampling theorem. And what does that say? That the sampling frequency, it must be greater than or equal to twice the highest frequency component present in the signal. So, f max is the highest frequency component present in the signal. So, the sampling frequency must be taken at least twice of that, more than that also can be taken, but the minimum sampling frequency will be at least twice of, it will be twice of the highest frequency component present in the signal, right. So, in the present problem already the signal is given and all frequency components are visible to us, right. What are there is they are just now we found in the part A that what are the frequency components present. So, what is the highest frequency component which is present in this signal? So, f max or the highest frequency component in the given signal. So, when we say highest frequency component, we are talking in terms of the frequency, not the amplitude, not the amplitude of the component, the frequency of the component which is having the highest frequency. So, in the present case this f max is 16 hertz, in the present problem it is 16 hertz, right, we can see from the table. So, that is why as per the Nyquist sampling theorem we will choose a sampling fs of, therefore we choose fs as twice of f max and that will be equal to 32 hertz. Okay. So, we are going to choose 32 hertz, correct. Of course, we can take more than 32, but the minimum but 32 would be adequate to sample the signal. And what is the difficulty if we do not satisfy this criteria? Then it will cause aliasing of the signal. What will happen? If we take fs less than 32, then aliasing will happen, right. Okay. So, we are going to look at one MATLAB based example today to demonstrate that how aliasing happens, that we will see, correct. So, as we study in the lectures if this sampling theorem is not satisfied, then aliasing will happen, right. So, remember if fs is taken less than 32 hertz, then aliasing will occur, which means that the signal will be incorrectly represented in the frequency domain. The frequency components in the signal will not be correctly identified if you take a frequency spectrum of the signal. The signal frequency will become will appear as a lower frequency signal, right. That is the problem with the aliasing, correct. So, I think this completes solution of example 3. Let us go to example 4. Let us go to next page. Let me write the question first. A signal given below is to be measured. Choose sampling frequency to avoid aliasing, right. So, let me write the signal now. X of t is equal to say 1 sine 2 pi 12 t plus 10 cos 2 pi 100 t plus unknown frequency components. So, let us solve this problem now. Okay. So, let me throw some light on this problem, right. So, you see this problem appears pretty much similar to our problem example 3, right, pretty much similar. In the example 3 also we were given the signal and then we were asked to choose the sampling frequency and of course guess the frequency components present, right. The part B we choose the sampling frequency. Now, here also we have to choose the sampling frequency and the signal is given, but there is one important difference. The difference is that in example 3 the signal given had all the known components, correct. That there was nothing, the signal on the right hand side you can see we could determine the frequencies of all the components. But in this particular example there are two components which are there, one is at 12 hertz and another is at 100 hertz, but then also signal contains some frequency components about which we do not have any information. It contains frequency components, but we do not know, it is not specified in the problem. So, this exactly typically is the situation in practice. We generally will not be aware about what are the frequency components present. and then we will have to measure such signals, correct. So, that is why now in this problem we are going to discuss that if such is the situation where the frequency components are not completely known, then how do you choose sampling frequency, correct, how do you choose sampling frequency. So, what is the challenge? Sampling frequency choice, to ensure that aliasing does not occur requires the knowledge of the highest frequency component in the signal, right, the components, the frequency component having the highest frequency, that must be known, and then we can choose the sampling frequency very correctly, and we can avoid aliasing. But if the frequency components are not known, how do you choose the sampling frequency? Because we do not know f max. This is the problem, right. So, let me write that here, that what is the challenge here? Challenge is that the component with the highest frequency is not known. So, Fs cannot be chosen to satisfy Nyquist sampling theorem. Okay. So, this is the issue, but let us now suppose that although there are components which are not known to us, but we know that from the given signal that okay, we would like to properly measure and analyze, right, the components which are known to us. For example, in the case we have 12 hertz and 100 hertz as the component. So, we would like that okay, these two components should be correctly measured. We are not worried about other frequency components. The only thing we need to be sure about is that those unknown frequency components should not corrupt our measurement and they should not lead to aliasing. That is our concern. Okay. So, therefore, what we want to do, so what is the task? Measure correctly the frequency components at 12 hertz and 100 hertz. That is our task. So, what is the solution? So, in fact, I discussed this in the lecture class that what we need to do, right. So, let us look at that now. So, what we do is that because we do not know the frequency components which are all present in the signal, and those frequency components can have any frequency. They can have frequency less than 100 hertz, more than 100 hertz, or both. There may be frequency components which are some less than hertz, some of them may be more than hertz, 100 hertz. All those things are possible. So, what we do is we make use of what we call as anti-aliasing filter, right. We use an anti-aliasing filter. So, you can go through the lecture to understand in more detail what is anti-aliasing filter, but just briefly I am going to explain that what we are going to do is we are going to pass this signal x of t, and let me abbreviate this anti-aliasing filter as AAF like this, right. And what is an anti-aliasing filter? This anti-aliasing filter is an analog filter. It is an analog filter, which means it works on continuous signal. It does not work on a discrete signal. Continuous signal it works upon, it is an analog filter, right, and then it gives an analog output which is the filtered signal. So, what we get here? We get an analog output which we are going to call as XFT, that is what we get, okay. And then let us suppose if h of omega is the frequency response function of this anti-aliasing filter, this anti-aliasing filter frequency response, if I show here the magnitude of this anti-aliasing filter, then this may look something like this. Okay, something like this. So, it means it has a flat response over certain range, and then after certain frequency f c, it removes the frequency component a great deal, right. The attenuation of the frequency components beyond f c is extremely large, right. So, that is what it is. So, it means that therefore, now f c is something we would like to choose, correct. So, what we do, so this is the cutoff frequency. Right. So, we choose the cutoff, we choose pass this x of t through anti-aliasing filter, and we choose the cutoff frequency, and then what cutoff frequency we take? We take the cutoff frequency as 1.28 times f max, correct, because there is a certain roll off. The filter characteristics, no, they do not abruptly truncate, right. That is why there is a roll off at the end, and that is why to take care of that roll off we take the cutoff frequency as 1.28 times f max, 28% more than the maximum frequency which we want to analyze, right. And then once we have xft, now we pass this, we record this signal in the analyzer, right. So, after this signal, then what we do, we can record this and pass it through the analyzer or any DAQ system. So, this DAQ system will then discretize the signal, right, and then it will give us XFN, the discrete version of the XFT, and obviously this would require the knowledge of the sampling frequency Fs, correct. So, this sampling frequency now, because XFT signal is the filtered signal obtained by filtering x of t, now we know the maximum frequency component present in XFT, because we have filtered it, and there can be no now frequency components beyond Fc, because that is the cutoff frequency of the filter, and that is why now for XFT we can choose the sampling frequency very appropriately, right. So, that is why we take the sampling frequency Fs as twice of Fc to satisfy the Nyquist sampling theorem, because now we know the f max for XFT, right. So, essentially we therefore get 1.28 times 2 times f max, right, which means it is 2.56 times f max, right. And in our case, what is f max? For the signal given, f max is 100 hertz, because we want to basically analyze those two components up to 100 hertz, right. So, that is why the sampling frequency then would be 256 hertz, correct. So, sampling frequency will be 256 hertz. So, that is what essentially would be the sampling frequency when unknown frequency components are there. That is how we can choose, I mean, is not it. That is why you see in practical analyzers always we will have an anti-aliasing filter, because in practice most of the time situation would be like that we will not know the frequency, all the frequency components which are present, and then therefore to guard against aliasing, we first pass the signal through anti-aliasing filter, which is analog filter, and then do discretization, because then we will be able to choose the correct sampling frequency so as to satisfy the sampling theorem. So, I think this is how this is done. Now, this completes the solution of example number 4. We now go to example 5. So, now we are going to have two MATLAB based examples. Okay, we are going to write MATLAB codes, right, and to implement some of the concepts we have studied in these lectures. So, now we are going to have MATLAB based examples. So, the first one is example 5. Let me write the question first. Find the DFT of the following signal using a sampling frequency of 16 hertz, right. So, x of t is equal to 4 sine 2 pi phi t plus 12 cos 2 pi 10 t, correct. So, this is the example 5. So, in this example, we are going to use a MATLAB script to compute DFT, and then we would see that if we use a sampling frequency of 16 hertz, what are the results. We would like to see what are the results, right, and let us compare with the frequency frequency components which are present in the signal. That is example number 5. Then the next example is example 6. Question: find FFT of the signal given below using Henning window function. X of t is equal to 10 sine 2 pi 70 plus 6 cos 2 pi 30 t, correct. So, of course, let me tell you what is Henning window function, right. Of course, this is also we are going to solve through MATLAB code, and for this problem let me tell you what is Henning window function. The Henning, we have studied in the lecture classes what is windowing, right, and what are windows, when do we use them, etc. We have discussed that all in great detail in that theory lecture classes. But for this problem we are going to use Henning window function, and let me tell you what is Henning window function. So, Henning window function is given by W of t is equal to half plus half cos 2 pi t upon capital T for absolute value of t less than or equal to t by 2, where t is the record length, okay. And then is equal to 0 otherwise. So, for other values of t, W of t is 0. So, the window function essentially describes a variation over a time length t, and outside that time length t W is 0. So, let us go to the MATLAB platform and let us look at the codes which I have written, okay. So, you can see this is the code for example number 5 which I have written, example for understanding aliasing, right. So, this example I have designed so that we understand that what is aliasing, and we actually compute the DFT and then see that is it showing aliasing. So, this code is essentially the same code which I have used earlier to find FFT in a previous session, right. there we earlier saw two examples. In one of the example we wrote a code for DFT and we found a DFT, complex DFT, one sided DFT, all that, and in other code we used the inbuilt MATLAB function FFT to compute the DFT, all that we have discussed. So what I am doing here is, you can see of course these are the statements to clear the MATLAB workspace variables. CLC is to clear the desktop from any data which is there, and closes all the figures which might be there, right, existing figures, right. And then now here I am it is given in the problem, choose a record length. So you use the record length 1 second, and the sampling frequency also has been given in the example as 16 hertz, that also I have chosen here. Then I am calculating the delta t, then setting the vector t t for computing the the discrete signal, right. This all we have studied in earlier example, and then this is the number of samples in the basically in the discrete signal, right. And then we have, I am calculating the frequency domain parameters. You can see here the frequency resolution, then maximum frequency will be fs by 2, right. And then I am finding the discrete signal. This was given to us in the example 4 sin 2 pi phi t. So in place of t I have substituted the vector of time, right, t, so that I get a complete vector of the discrete time, plus 12 cos 2 pi 10 t. Then this is the program for DFT which we have used in the earlier example in an earlier session. This is the same example, same code, I have just copied it. Then I am finding here, you can see the one sided DFT, that is something we are going to see the results for, right. And then after this I am plotting the figures, right. The first I am plotting the continuous signal which I have obtained by sampling the signal at a very high sampling frequency, much higher one than 16, right. And then I am plotting the time signal and overlaying on it the discrete signal which was obtained at 16 hertz, and that is the time signal. And then I have this is of course I am plotting just the discrete time signal, and then I have, now here I am plotting the single sided DFT, right, single sided DFT I am plotting, and that is it. So that is nothing but the code, right, which essentially is the same code we have used in earlier example. The only difference is that now we are using a sampling frequency of 16 hertz as given in the problem and a record length of 1 second. So let us run this code. Let me hit the run button here, and now program is running as shown busy here. The program, okay, now it is drawing the figures. So let us look at the first figure which is a overlay of the continuous signal and the discrete signal, right. And the blue one is the continuous signal, and stem signal shown by the red stems, that is the discrete signal. And so this is sampled at 16 hertz, and then this is only the discrete signal which has been recorded. So this is the data which is there with us, and we are processing this data to obtain the single sided DFT. So now I am going to show you the single sided DFT which is obtained from this discrete signal. So this is the plot of the single sided DFT spectrum, and you can see here that now it shows two frequency components. Of course, because Fs was 16 hertz, the sampling frequency, that is why the frequency range of this spectrum is 0 to 8 hertz, 0 to Fs by 2, right, that is the frequency range of this spectrum. So and there are two frequency components which are seen. One is at 5 hertz, correct, and it is correctly identified because there is a signal at 5 hertz in the given signal and of amplitude 4. The second component is shown to be at 6 hertz, which is not correct, For example, you go back to the our program, you can see the second component is at actually 10 hertz. Second component is at 10 hertz. You can see first component is at 5 hertz and second component is at 10 hertz. But the signal, what does it show? So this figure shows that the second component is at 6 hertz, which is not correct. So what has happened is that because the sampling frequency is 16 hertz and the maximum frequency component is 10 hertz, So, the choice of sampling frequency is inadequate, it does not satisfy the sampling theorem, and that is why it has led to aliasing of the those components which do not satisfy the sampling criteria, sampling frequency criteria, and that is why the component at 10 hertz has got aliased, and now that 10 hertz component is appearing as a 6 hertz component in the spectrum, that is nothing but aliasing, correct. So, this aliasing has the problem that high frequency components which do not satisfy the sampling frequency criteria, they get aliased as low frequency components, and then they get mixed with the genuine or the true low frequency components which might be present in the signal, and they distort the low frequency basically spectrum. So, that basically gives a misleading representation, an incorrect representation of the spectrum. So, I think this clearly demonstrates the problem with the aliasing. So, then now you can see here just to further demonstrate, if I use a sampling frequency of let us say 20 hertz, right. Let us say if I make it, you can see here instead of 16 now I have made it 20, right, and if I run this program, we hope that because the highest frequency component was 10 hertz and 20 satisfies the Nyquist sampling theorem, we must get a correct indication of the both frequencies. Let us run this. That is the result. You can see the DFT. Now you see there are two components, one at 5 hertz as we got earlier as well, and now there is the component at 10 hertz of 12 units amplitude, and that correctly identifies the second frequency component as well. So, this clearly shows that with a proper choice of the sampling frequency, aliasing can be avoided. Let us make a third run further just to show that if I take even higher frequency, what happens. If I take 64 rather, instead of now 20 I am taking 64, which is quite more than the necessary sampling frequency. So, let me run this. Right. So, what we see again, we have components at 5 hertz and 10 hertz, and there are no other components, right. So, this again very correctly identifies the frequency components, their frequencies and amplitudes. So, this shows that if we take sampling frequency more than the minimum desired value, still we are able to it will give you a correct identification of the frequency spectrum, but the minimum we require is the one which satisfies the Nyquist sampling criteria. So, this completes our example 5. Now, I will now open the code for the example 6, right. So, you can see this is the code where we are going to basically study FFT with windowing, and let me explain the code first. So, this is already I have explained you all these statements, and now here I am taking a record length of let us say 1.5 seconds, correct. So, the idea is that in practice what happens is that we would not know the frequencies which are present, we would not know the time periods of different frequency components. So, even if the signal is periodic, we would not know what is the period of the signal, right. And other thing is that because the in practice often there will be small variation in the frequencies. The frequencies, for example, if there is an electric motor, right, and which is generating some vibration, and we are measuring that vibration, and those vibrations are periodic because the excitation forces generated by the motor will be periodic. So, we expect periodic vibrations, but the issue is that because of small voltage fluctuations etc., the speed of the motor may vary, and hence the periodic vibrations their periodicity varies. So, even though vibrations are periodic, right, and if we know the rotation frequency of the motor, one may say okay, I approximately know what is the time period, but the difficulty is that because of the small fluctuations in the operation, the frequency and the periodic signal will keep on varying. So, even if you choose at some instant the periodic if you determine the period and choose the sampling the record length, there is no guarantee that this period will ensure the that you are able to remove leakage, right. So, therefore, because of the variation in periodicity also the leakage may happen for a certain choice of the time the record length. So, that is why this example demonstrates the difficulties which are faced in practice. So, although the signal is given to us, but we are choosing a record length which basically something arbitrary like 1.5 second, right. So, I have taken 1.5 second as the record length here, and then sampling frequency is 32 hertz, and this is all same basically till here. This is the signal which is discretized, which was given to us, and then now we are finding FFT. So, now we will find FFT for two signals. First we will find FFT without any window, we will not apply any window function, which essentially amounts to using a rectangular window, hypothetical window, rectangular window, and after that we will apply window function to the signal and then find its FFT, and then we will compare both the windowed signals, signal without window and with window, and we will also compare the FFTs we obtained for signal without window and signal with window. Let us do that. So, the first thing is, you can see I am just finding the FFT of the signal without window, and this is the same program I have used in our earlier example, right. I am just using the MATLAB FFT function, FFT, passing it the signal x. So, when I am passing signal x itself, which is the discrete signal, then I am not using any window function, right. It is like using rectangular window, and then I am calling and storing that single sided FFT as fyk no window. In this variable I am storing the FFT yk no window. After this, now I am finding the FFT with window, okay, you can see here. So, now first I am defining the Henning window, because that is what specified in the example that use Henning window function. So, I am just you can see I am writing here Henning window function. So, in place of t I am writing tvac, so that it will find a discrete window function signal over the record length t, right. So, it finds a discrete window function, and then I am multiplying the original signal x with the window signal. You can see on the right hand side I am using the command x dot star window, because x is a vector here, w is a vector. So, I am multiplying the element by element, these two vectors, right. So, when I use the symbol dot, it basically indicates that we need to multiply the vector x and vector w at the element level. Once that is done, I get a new vector xw, which is the windowed signal, right. Now, remaining thing is same, I am just finding the FFT of this xw, right, and then I am storing the single sided FFT of this xw in this manner in the variable yk window, right. So, now we have two FFTs, yk no window and yk window. Now, this completes our all data processing. Now, we are going to draw figures. You can see this is the first figure where I am plotting the window function. I am just plotting the window function on the time axis, and then after this I am plotting the discrete signal without and with window. You can see here I am just comparing the discrete signal without and with window. So, I am announcing a figure, and then now I am making two subplots here in this figure. So, what is the command to make subplot? So, I am making a subplot. So, this command is, first I am giving the indices 2, 1. 2, 1 means divide the figure into 2 rows and 1 columns. That is the meaning of this, right. 2, 1 means it represents it requires that the figure should be divided into 2 rows and 1 column, and then the last one indicates that I am currently utilizing the first of those matrix of figures of plots. So, of the 2 rows, the first row we are going to plot the signal without window, okay. So, subplot 2, 1, means divide the figure into 2 rows and 1 column and use the first row of that. And now here you can see I am making a stem plot using of the signal without window x. After this, now I am announcing subplot 2, 1, 2 means the second row of the figure, and then I am plotting here the xw, that is the signal with window I am plotting. So, it will make a basically a single figure, right. After this, now we can similarly make figure with two subplots here you can see 2 comma 1 comma 1, and I am comparing here now the FFT without and with window, and I am making here H stem first of all the absolute value of the FFT without window, and then in the subplot 2 comma 1 comma 2 I am making a stem plot of the FFT of signal with window, right. So, that essentially completes our code. Okay. So, let us run this code now. I press the button run, it is busy computing it, and now it has made the figures. Let us go to the first figure. So, the first figure is simply the plot of the window function. So, this shows the Henning window function. So, at the extremes it basically makes the signal 0, right. That is what essentially is done in windowing as we study in the lecture classes, right. And then now we are going to look at the second figure, which compares the signal without window and signal with window. So, the upper figure is, you can see on the y axis I am writing x here, which is the signal without window. So, this is the this red stem plot shows the signal without window. At the bottom the stem plot in blue shows the signal with window. You can see on the extreme ends the signal has been basically made to decay to 0, right, at the extreme. Now, let us look at the FFTs. So, on upper side shows you the FFT of the signal without window, and what we notice, the rate plot stem plot shows the FFT of the signal without window. What does it show? It shows that there are large number of components appearing. Of course, at 5 hertz we see there are components appearing, the signal has at 7 hertz the signal, the frequencies are 7 hertz and 13 hertz in the given problem. So, at 7 hertz and at 13 hertz we see peaks. So, that is correct, right. It shows that there are components with significant amplitude at 7 and 13 hertz, that is correctly identified. However, you see several such rate stems even at 0 hertz, 1 hertz, 2 hertz, everywhere. What are these components? They are not actually present in the signal. However, they essentially essentially is the effect of truncation of the signal because of the the starting and stopping of the measurement process from 0 to 1.5 second. So, because of truncation, as we studied in the lecture classes, that time domain multiplication of a signal with a rectangular window leads to frequency domain convolution, and that gives rise to many spurious frequency components around the true frequency components. And that is why these small rate stems you see, they are all because of the leakage, the leakage of the energy from the true frequency components to the neighboring frequency components. So, this is all leakage you see here. Now, what we have done, we have now also found the FFT of the signal with window. We multiplied the signal with window function and found its FFT, and the lower plot shows you that. And what is the result? What is the observation? If you compare the two plots, we see that in the lower plot, which is obtained with window, the the spurious components have been significantly being attenuated. There is a significant attenuation of the spurious frequency components. So, you see this at 0 hertz, 1 hertz, 2 hertz, 3 hertz, 4 hertz, all components have been significantly attenuated. Even so components at 10 hertz, 11 hertz, they have been significantly attenuated, and that is why leakage has been substantially reduced because of the use of window. So, that is the advantage of using window, right, when we do not know the time period of the signal, which is typically the situation in practice, right. So, Henning window is generally used for continuous signals, not for transient signals, right, and as we study in lectures, for transient signals we use, for example, exponential window, but for continuous signals like periodic signals, random signals, we may use Henning window function, one of the important window functions which can be used to reduce leakage. So, this basically completes the solution of example number 6. So, you can see in this manner now we have solved today 6 examples, of which 2 examples were based on MATLAB, right. So, I think now we can stop here. Dhanyavad, thank you.